Well, good morning, dear, and welcome back. So, today we are going to discuss another very important machine learning model or tool or algorithm, whatever you want to call it, the name of which is logistic regression. This is widely used and based on very fundamental um, considerations, right? Widely used for classification problem. And as you know, if you do not know, now you should know that in machine learning, deep learning, we have two basic or fundamental problem. One is called regression problem. Regression problem. What it is? For any x, okay, y is continuous. So I have say data like this, okay, and I am fitting my hypothesis, okay. So fundamental assumption is for each x there is a y. So y space is continuous. Taking the example of housing price, if this is the floor area, x is the floor area, is featured. So for each x value, we have a price of the house. Okay. So y space is continuous. Although practically this is not perfectly correct, because you see, if 600 square feet house costs some x million rupees, then 601 square feet or 599 square feet perhaps will cost the same price. Okay, but we'll assume on many applications this assumption is perfectly fine, that for each x you can get a y. So y space is continuous. Whereas in classification problem, so what is a classification problem? Y space is discrete. Say, I have a binary classification problem. Say, y can take only two value, y equals to 1, y equal to 0. Say I am trying to classify between two classes of house. For example, if the floor area is beyond something, say 800 square feet, then it will be considered classified as a luxury car. Or if it is less than 800, it will be classified as a people's house, or people's house, luxury house, people's car, luxury car. Based on sizes, we can define a classification problem where for each x, say up to 800 square feet, everything belongs to people's house, and beyond 800 square feet everything belongs to luxury house class. Okay, so this is essentially a classification problem where for when the x is continuous, y is discrete. It could be only 0 and 1. Also, you see, I can give you an example of multi-class problem. Okay, so you see, what is the classification for some x? Okay, so some x, yi is discrete in nature, 0 and 1. Or it could be multiple classes also. Say in your class you have a grading problem, right? F is fail grade, D is merely pass, C is well fair, B is good, say B plus is very good, or okay, so this is A is excellent, and beyond excellent is exceptional, maybe. This is A plus grade. So here you follow, A plus is excellent, this is good, this is B plus is actually, this is A is very good, B plus is good, then B is say good, C is fair, D is pass, and F is fail. Okay, so these so many grades are there, right? And how we classify our students. Say, if somebody is getting less than 40% marks, I don't care, he or she can get 30%, 20%, 10%. Below 40% will be classified as F. So you are understanding? Although one can get any marks from 0% to 40%, her or his class will be F only. So discrete, okay? Similarly, is the case, say somebody is getting 40 to 50% marks, then her class will be D, then 50 to 60, her class will be C, say 60 to 70, her class will be B, then 70 to 80, her class will be B plus, then say 80 to 90, class will be A, and beyond 90%, 90% and 100%, right? So A plus, like that. So this is an example of multi-class problem, right? While an individual can get any marks from 0 to 100, but her class will be discrete in nature based on what marks she has got. Okay, so you understand. So this is a multi-class problem example. This is a binary class problem, 0 and 1 class problem example. In all these, for continuous feature value or x value, you have only discrete output or y. Okay, so this is a classification problem. And this classification problem is widely used for classifying, as I said, luxury house, um, then people's house, people's car, luxury car. Then in email classification, it could be two class spam. You are getting a lot of spam or ham, not spam, right? Online transaction could be fraudulent and non-fraudulent. A tumor can be based on size, can be malignant or benign. So all kind of problem which are practically very important are classification problem. Okay. Now we need to develop a model which can solve our classification task. Now to do that, let us ask ourselves a question. We have already learned linear regression model, right? And in detail, how to you have data and how to design a hypothesis and how to use that hypothesis, so that and also you have now knowledge that okay how the hypothesis could be a best fit hypothesis, not underfitted, not overfitted, all kind of thing you know. So why can't we just extend the same technique of linear regression model? Technique means designing the hypothesis. That means you need a loss function or cost function, whatever you call. Okay, and we had a mean square error function, so use that, and then you can use an optimizer which will work on that cost function and you will give you the parameters, right? W0, W1, W2, all kind of things. So you know, right? Linear regression model. Let us try to use the same linear regression model for solving our classification task and see what happens. Say, so stay tuned. So we have, say, floor area. We have just taken this as a feature, and then we have two classes of house: people's house and this is luxury house. And in between, we have decided a threshold 0.5 in between that, and say we are just formulating our problem. Say if, because without formulating problem you cannot classify, right? You will have to formulate that in our grading system that beyond 50 one should get C grade. Similarly here, beyond greater than 800 square feet, it should be classified as a luxury house. Less than 800 square feet, it should be people's house. So this kind of classification formulation we'll have to do based on the data. Say we have done this, okay, and say this is our maximum floor area. It could be 800 square feet or 800 square feet. So if it is less than that, we are classifying all the houses as people's house. So this is class people's house. And this is our class of luxury house. Okay. So I have data only, data about the floor area. And say you have collected this data from that people's house class, and you have collected, say, this data from luxury house class, and then this one is the regression line which you have fitted using same hypothesis w0 x0 plus w1 x1, like that. Okay, so this is your predictor, and then you are very happy. So I have a predictor, and then you see um, I am having some sample value. Okay, if it is here, so this is 0.5. So this is cutting this predictor line here, which is less than 0.5. So anything less than 0.5 will be classified as people's house, that is y equal to 0, and anything beyond 0.5 will be classified as luxury house, like that, right? We have decided to use only a threshold to classify whether a house belongs to luxury house category or people's house category based on threshold which we have determined. Okay, zero point 0.5, it makes sense, right? 0 and 1 you have to class, and in between we have a threshold 0.5. So there is no rocket science here. Okay, so far so good, and you are classifying very happily. Now suppose your friend has collected different data sample following this same grammar, means merely she has collected this samples. These are also, of course, data which is less than 800 square feet. So they belongs to people's house class. And suppose she has also collected this data, these samples. These are also definitely, as your definition suggests, so beyond 800 square feet, so they are beyond 800 square feet. So they all belongs to our luxury car. So these are now our, these data are now our people's characterizing our people's house, and these are the data characterizing our luxury house. Right? And then if you just use the same regression analysis model, you will get a line tilted because it will try to capture the train of the data, right? So you will get a hypothesis here. And of course, what will happen? So this is my threshold. Now threshold will be shifted. So that's the point you need to know. Okay. So what is happening due to shifting this threshold? You see now, if somebody is using this is also correct, right? Because this regression line has samples following same grammar, all the samples less than some samples in the people's house category, some samples in luxury house category. Simply they are different, right? But they belong to the same class, right? Nothing, no wrong doing. Now, because it is regression line, now you see the threshold has shifted here. And what is wrong here, you see? Since threshold is shifted here, now this, what is going to happen to this kind of houses? So these houses, of course, are greater than 800 square feet. And now, based on this regression line, they are still classified because everything, this is a threshold line, everything here is people's house, everything here is luxury house. So these data now, which earlier compared to this regression line, okay, this data crossing the threshold value, they were actually rightly classified because beyond 800 square feet, they were classified by this regression line as luxury house. Now this regression line will classify them as people's house. You can see, because they have not crossed this threshold. Okay, only here, say it could be 1000 square feet, I do not know. Only here, this regression line will classify them as luxury house. Here, they're classified as people's house, which is wrong, isn't it? So, why it is wrong? Because either this one or this one is wrong. And you can land up these and maybe in between many regression line, because there is unbounded data. You see, I have only told everything which is above 800 square feet is classified as luxury house. It could be 800, 900, 1000, 2000, 3000. So upper bound is not given. Okay. Here also I have told that anything less than 800 square feet will be people's house. I have not talked about what is going to happen to 799, 700, 600, 500, 400, 300 square feet, right? So this lower bound is not specified, upper bound is not specified. That's why the designer, based on the kind of sample he is or she is picking up from the two classes, his or her regression line will be non-unique, and they are all correct. But they are incorrect when we are using them in practice, isn't it? Because you see, if this is correct, this is incorrect. If this is correct, this is incorrect. Because this is classifying, this is correct actually, based on our initial assumption that anything based on that we have actually marked anything 800 square feet, more than 800 square feet should be a luxury house, and this is doing that. But here this regression line will shift that threshold, that 800 threshold here. So earlier, so you understand, right? So you are getting ambiguous result. Earlier, these houses, say 900, 850, 1000 square feet, whatever, I don't know, they were classified as a luxury houses, but this regression line are classifying them as a people's house. So there is something wrong. Eh? That's why it's the inherent problem of regression model that they cannot be used as a classification model. So we need to actually make a bound. Okay, we need to develop, design a function or algorithm which will restrict our hypothesis. Okay, and this restriction should be between 0 and 1. So we have understood why we can't use the same linear regression model which we are very enthusiastically studied and designed. It's a great tool for regression, but for classification it failed miserably because many regression lines are classifying the same task into different classes, which is not acceptable. So we need a tool called logistic regression tool. So why it happened? Actually, this is our hypothesis in case of linear regression. Since this was unbounded, this gave ambiguous result, okay, which we could not use. So that's why we are thinking of, see, this is intuition, you see. For logistic regression, let us modify the same hypothesis as some function g of w transpose x. X is a feature, of course. And say this is putting this as z. So we are actually making this hypothesis as a function of z or w transpose x, such that g of z equals to 1 by 1 plus e to the power minus z. So this is a function which is, sigmoid function, which we have used for restricting this hypothesis. Why this restriction is needed, you have studied earlier slide. Now, what it is actually doing? You see, this this sigmoid function, the nature of the sigmoid function is this: it has two asymptotes, one at 0, another at 1. If you see, you can put that putting the value, you see z equals to 0, z equals to 0, then you are getting e to the power 0 equals to 1, 1 by, so you are getting, this is 0 0.5. Huh? So anything less than 0 will be here, all the data will be here. Anything greater than 0, all the data will be here. So now, as if the function has two hands, and forcibly, you see, forcibly, this data were actually, you see, separated by only a vertical line. Now forcibly somebody is actually taking those data and then clearly segregating them along the two asymptotes. That's the advantage, you see. So everything we have passed through this sigmoid function, and since it has two asymptotes, all the data belonging to our luxury car now will be clearly separated, no mix up. Okay, so earlier actually it was like this, and immediately from here the people's car were starting. No, here they're clearly separated, and the problem of misclassification is solved. Now it is, you can see that this is my hypothesis, okay, equals to 1 by 1 plus e to the power minus w transpose x. This is actually makes a decision by calculating the probability. It is calculating a probability. You give any sample, and suppose I know how I will know that I will discuss in my subsequent classes. Suppose I have designed and I know the parameter. So parameter w is known, and then giving any sample x, you will get some value that is given x, probability for some w, okay, for some w, this h is actually calculating the probability that that sample belongs to a class 1. If the probability is more than 0.5, yes, it belongs to class 1. If it is less than 0.5, it doesn't belong to class 1. So it belongs to, since it is binary class, it belongs to 0 class. Okay, so that's how we have achieved that. We are calculating, my hypothesis is now calculating the probability a sample belongs to a class 1 or 0, that is whether a particular sample 800 square feet or 900 square feet. So 800 square feet, if it is 800 square feet is 0.5, then you will see the value will be 0.5. So it is neither, means it is at the boundary, okay, between the two classes. And then for all other samples, either it will be greater than 0.5 or less than 0.5. And this is the making minus w transpose x, okay, greater than equal to 0. This calculates the decision boundary. Okay, so now if I have two classes, say these are all our people's house and these are all my luxury house, then this actually is giving my decision boundary. Okay, so w transpose x equal to 0 will give the decision boundary, okay, and h is calculating the probability that a particular sample belong to which class. So this is the function we have brought, and we have encapsulated our raw hypothesis which we design in our linear regression inside that function, so that now we have a restriction to this. It only can, the function value can only lie between 0 and 1. This is the nature you can see, okay. And so this can only lie between 0 and 1, and my misclassification problem is gone, okay. So since this is for binary classification, I can design such curve. Then the thing is, even if you have a multiple classes, for example, like this, one good thing about multiple class is that I can reduce them into a binary class problem. Say, I want whether a student has got A plus or not. So I don't care if a student is coming with say 80% marks. I don't care he or he should be classified as A, or I will simply say it is non A plus. So if somebody has scored 90% A plus, so A plus I am calling my class 1, and all other class 0. So my purpose is served. Or suppose I want to see that how many students got just pass mark. So I will make my interest C grade and non C grade. Or how many failed. So I will focus my interest on F grade and non F grade, like that. So multi-class problem for all practicality can be actually model as a binary classification problem. And for binary classification problem, now we have a beautiful function called sigmoid function or logistic function. Okay, it has a name which encapsulate our linear regression hypothesis inside the function and calculate the probability that giving a sample belongs to a class 1 or no, or 0, without any ambiguity. So class 1 and 0 we call it in logistic regression model. Don't worry about that. That's two class actually, positive and negative class. You can call it in support vector machine. Don't worry about all these notations. Various tools has used various notations in support vector machine, which is another elegant classifier. We will study two class are denoted as +1 and -1. Here it is 0 and 1. So all kind of thing are there. So simply by making this design, we have now able to solve solve the ambiguity of our linear regression model. Okay, so you see what this function now the hypothesis is actually calculating. Explicitly, it is calculating the probability, right? A given sample belongs to a class. Okay, and implicitly, it is calculating the decision boundary. Okay, because here you see, if this guy, right, if it is 0, then it is threshold, means in which class it belongs, ambiguous. Greater than 0 means whatever your it's minus, right? Greater than 0 means it belongs to here, less than 0 belongs to here. So you see, predictor predict y equal to 1 if W transpose greater than 0. It will predict y equal to 0 if W transpose x less than 0. So beautiful, right? So, and you can just see that this is a decision boundary which implicitly you are getting from the sigmoid function itself. And what it is doing, as I told, it is just separating the two samples of the two class along the two asymptotes. And you now will have to design parameter, right? So suppose the parameter again is like this, and this value is some value you have got, -5 to 1. So your decision boundary will be 2x plus x2 equal to 5, which is this deadline. So this will classify actually anything beyond this deadline here. So it will be less than 0.5, and they'll be classified as belongs to people's car, for example. Anything here will be classified as a luxury car, like that. Okay, and if of course the data are nonlinear, then also if you can capture, design your hypothesis like this, okay, and say I have, right, I have not yet told how to get the parameters, right, and that's another very interesting story we'll discuss in our next class. Suppose you have got that parameter, then this is actually the decision boundary is a circle. So clearly, so you have two classes which is nonlinear in nature. By suitably designing the hypothesis, you can even make a very linear decision boundary. Okay, and incorporating various higher order term. Okay, you can also make a very peculiar shape decision boundary. It may be overfitted problem, right? And same old story, overfitting, underfitting, we'll discuss. But if required, you can make a complex decision boundary and classify your samples. Okay, so today we have understood what is regression, what is regression problem, what is classification problem, why linear regression cannot solve the classification problem, and why we have invented a function called sigmoid function, where it was existing in mathematics but we have incorporated here and solve the problem of separating the samples which are belonging to the two classes into two asymptotes, and then our problem of classification solved, because if you have a sample, directly you fit to the hypothesis and it will calculate probability. If the probability is more than 0.5, it belongs to positive class, less than 0.5 it belongs to negative class, like that. And implicitly also, you see, W transpose x equal to 0 gives you the decision boundary critical to the 0.5. Okay, that is the decision boundary. Beyond that, everything is 0 class. Above that belongs to 1 class, like that. So you can design the predictor, but you will have to encapsulate it with logistic function, and then definitely you can solve the classification task. But we have not yet discussed how what will be, because you know this is a machine learning model, right? Like linear regression, here also you need to have a loss function or cost function, because that will give you parameter, and there also you need to run optimizer. Okay, so we have not yet talked about how to design. Can we use the same cost function, and if not, then how to design a cost function which may preserve the beautiful characteristic of convexity of linear regression model. So all this very interesting story we are keeping for the next class. Till then, stay safe and have a nice day. Bye bye.